Hi, welcome back to our class notes on the Intro to Rational Functions, which for those of you in pre-calculus is a review of what you learned in Algebra 2. Super important for functions in calculus, so we decided to continue our review here at the end of 2020 with a review of rational functions. And this one is kind of going back to some stuff we did at the beginning of the year. So we're going to be looking at the restricted values, the restrictions of the rational function, your domain, using, of course, correct set notation for that, and then you're finding your x and your y intercepts, all things that you should be very familiar with. So what I would like you to do right now is go ahead. We're going to let you do, again, some work because this is all about you just reminding yourself how to do things. You're going to plug in 0, -2, and 3 into this function f of x. Then I would like you to, once you find those values, you're going to completely factor it, which is what we've been practicing in prior videos. I would like you to tell me, what do you notice about the results of 2 of the 3 function values? So there should be something that's the same about 2 of them that's a little different. And kind of stop right there. I'll throw up some questions in the Edpuzzle for you guys to answer, but let's have you guys do that, and then we'll come back in. Okay, so coming back in, and the 2 values that had something similar happen to them would be -2 and 3, and those values made the function undefined. The f of 0, I'm just reminding you for your review here that when you plug 0 in for x, that what you are actually finding is your y-intercept. And so that was kind of important for our y-intercept. We're going to talk about that in more detail. When you go to graph a function, it's kind of important to know where your y-intercept is. All right, so we can see also down here that we did go ahead and simplify. We factored our equation, and our equation ended up being 2x plus 1 over x plus 2 with an exception, okay? And remember that for future reference, that this is what I have been calling Fred, and Fred's going to have a lot of the answers when we go to graph our rational function. So I just want to remind you that that's our reduced function right there. And also down here that the 2 values, -2 and 3, are values such that the denominator was equal to 0. And since division by 0 is undefined, the function f of x would be undefined when the denominator is equal to 0. We call these restrictions of f of x. So that's kind of important in terms of terminology that we've used in the past. And I went ahead and defined the value of x for which a function is defined is what a restriction is. Now, it happens in many scenarios, like square root of a negative is undefined, division by 0 is undefined, log of a negative is undefined, log of 0 is undefined. So there are many cases where you would get an undefined value in functions, but in rational functions, specifically in rational functions, they only occur when the denominator is 0. I'm reminding you that a rational function is a polynomial divided by a polynomial. All right, so looking down here is the graph of our function. And I will say, kind of looking at it, you see here at -2, we have a vertical asymptote. So I'm going to go ahead and simply just make that a dotted red line. And then also, I'm going to go ahead and leave it in red, but there's a hole over here at that. So the type of discontinuity is we have an infinite discontinuity at x equal to -2. We have a point discontinuity at x equal to 3. And I'm going to remind you, kind of if we look at the graph of the 2 restricted values, I guess I'm just going to list those things over here. So x equal to, -2, vertical asymptote on the graph, which implies an infinite discontinuity, and x equal to 3 is a hole on the graph, which implies a point discontinuity. Now, the other thing that this implies, kind of as we're looking at it, that's going to kind of go back and look at it, the point discontinuity must have been removable, and the infinite discontinuity was non-removable. And so kind of when we look at that, like if we come back up here to the top and we take a look at what we have, our f of -2, which was the non-removable one, notice that we got a non-zero over 0 form. So that was kind of related to what we talked about before. And that in this one, we got a 0 over 0 form, that what's called the indeterminate form. And that indeterminate form is that indication that it is probably removable. It's not 100% removable, but it is probably removable when you see that. And by removable, what we mean in this case is we were able to remove the factor that was called the bad guy factor. We were removing that factor and getting it out. And that's the idea, that we were able to remove the division by 0 through a algebraic process, in this case factoring. It caused us to have an exception down here, and having that exception is also an indication that you have a hole or a point discontinuity on the graph. Now, keeping that in mind, so we have two values for our domain. Now, when we write our domain, there's two ways to use it. You can either do set notation, the set of all x, and when we do that, whoops, sorry, let me scroll down here for you. The set of all x such that, remember our little line that means such that, and I need to get this thing to work for me. Come there, come back. There we go. All right, so such that, and we kind of assume in set builder notation that x is a real number unless we state otherwise. So we can simply go x such that x does not equal -2 and 3. So we can kind of add those in as our restrictions that we are going to take out of it. And then the other way that we could write this is we could write it in interval notation. So we'll say or on that one. And when we write it in interval notation, because we want to take them out, we are going to use parentheses for that. So why don't you guys go ahead and try writing it while I write it. I'm sure mine's going to take a little while to catch up to me because my computer is being a little slow. So you guys can write it while I am writing it. And I'm going to see if I can fix this right now. I don't know why if I have to click off and click on, it usually changes it. All right, and then so you can check yours with mine. Notice that I had to do 3 intervals because when you're looking at it, you have 3 pieces to this graph. There's this piece here that approaches the vertical asymptote. So I'll use it with this. So here's the first piece, approaches a vertical asymptote. It has a horizontal asymptote. We'll talk about those in another video. And then we have the second piece, which is here, which has a hole, and then the third piece goes from here over. So we have those 3 pieces that we're taking a look at on this graph. All right, so the next thing that we're going to do is I have given you 5 graphs below. So if I'm just going to scroll down, and there are 1, 2, 3, 4, actually 4 graphs below. So in the 4 graphs that are below, one function is different from the other 3. So I would like you to identify which function is different, and then I want you to state 5 ways that this function is different from the other 3. And I'm going to ask that in the Edpuzzle, and then we will come back and discuss. All right, so coming back in, let's kind of talk a little bit about these things that were different about h of x. That, when we look at all of these functions, they're all a quadratic divided by a quadratic. So they're very similar in nature, and quadratics, of course, each have 2 factors. So there will be 2 factors in the top, there will be 2 factors in the bottom. And that's something that's very similar about all 3 of them. But what you'll notice, the first thing that I had you talk about was the idea that h of x has 2 vertical asymptotes instead of like the other ones that they had 1. So kind of thinking about the removable versus non-removable, h of x, when I go to factor it, should have two factors in the denominator, none of which are going to cancel. The minute that you see the two vertical asymptotes, you know that the factors in the denominator were not removable and did not simplify out. H of x also did not have a point discontinuity like the other three graphs. And again, that's getting to that idea that the other three graphs must have had factors that canceled out as we were simplifying. Now, this one's an interesting one because we haven't really talked about this yet, and I don't know how much you talked about that in your Algebra 2 classes, but h of x crosses its horizontal asymptote. If I look at that below, again, let me get my computer to catch up with me. Sorry about this. I think it's in the morning that we have more difficulty when I'm doing videos. So crosses its horizontal asymptote. So if I come down here and I take a look at h of x, right here, oops, that was kind of, well, you didn't even see it, so we'll put a dot right there. So that when you look at where it crosses, oops, here we go. So I'm looking right here. So you have the end behavior is approaching here, and it crosses that horizontal asymptote right in that location. Now that's something that you may be uncomfortable with because you're so used to the statement that you do not cross the asymptote, but the only asymptotes you don't cross are vertical asymptotes because vertical asymptotes come from domain restrictions. Horizontal asymptotes are a little different in that they're really only describing the end behavior of the graph. And so the idea that you could cross it in the middle, it's perfectly fine to cross horizontal or slant asymptotes, if you talked about those in Algebra 2 as well. Our last two things here are this idea that our h of x, because it had two non-removable discontinuities, it has three completely separate pieces. And whereas the other ones, they all had three pieces, but two of the pieces were kind of joined right where the point was. So they weren't distinct separate pieces. And what you're also going to see when you take a look at this on, say, a calculator or even in Desmos, you oftentimes will not see the hole. You have to know the hole is there because it doesn't show you that unless you click on it or you hit trace on your calculator. And then the other thing is that you had two x-intercepts on your h of x while you only had one on all the rest of them. And that had to do with the fact that when you remove a factor out and cancel it, once it's gone, it's only the non-canceled factor in the numerator that gives you the 0. And so h of x still, of course, had two factors in the numerator because nothing canceled. All right, so to finish out this video, what I would like you to do is to go ahead and kind of do this summary for us. So we're going to rewrite the function in its completely factored form. And these are referring to, I had the page number wrong on your sheet. I forgot to edit that. But I'm referring to the ones back here. So you do want to go ahead and rewrite the function in completely factored form. Identify your domain. I don't care what notation you use, just a correct set notation. Set the non-canceling factor equal to 0, state the zeros, give me the value of the constant term of the numerator over the constant term of the denominator, which is really kind of plugging in x equal to 0, and then using that to get of the y-intercept. And then what you're going to do is you're going to scroll down here and you're going to answer these questions in this table. And then we will come back next class. I think I'm going to stop right here for today. And that will kind of be your quote unquote homework, is to go ahead and finish that up so that when you come back in on the next class period, we'll go over those and kind of discuss that. So I'm going to go ahead. I'm going to end this video for, this is, I believe, on the 20th of May, our little COVID-19 lessons. And I appreciate all of you who are hanging in with me and doing your job and looking through these videos. Go ahead and finish up just this section right here, and then we'll be done for the day and we'll pick up next class.